Numbers are meaningless without units. This is true everywhere, from engineering applications to day-to-day life. If you asked your friend how far away is the grocery store and your friend just told you 3, you might wonder, 3 what exactly? Is it 3 kilometers? Is it 3 miles? Because having to walk one of those distances will feel considerably different than the other. And this is where the importance of units comes in. Not only is it important to quantify things using units, but one must also take care to use the correct units. Using incorrect units can have consequences varying from minor inconveniences to expensive to potentially disastrous. Just take the Gimli glider for instance, an aviation accident that occurred as a result of incorrect units being used. Now this is an interesting example I'll come back to later in the video. But all of this is to say that having a solid understanding of how to work with units is necessary in all applications involving numerical calculations. So, let's talk units. In this video, I'm going to cover the following: the basics of units, converting between units, metric prefixes, and finally, uncertainty. What is a unit? Simply put, a unit is a predefined size of some physical quantity. This defined size can then be used to make measurements of that quantity. Let's say that we want to measure some quantity like length, for instance. We can use meters as our unit. The meter has some defined size. Alternatively, we can use feet as our unit. Feet also has a defined size. That's different, however, from meters. If we were to measure a table and it was 2 meters, if we were to measure that same table using feet, we would get something numerically different. We'd get 6.56 feet. This is because the size of a foot is different than the size of a meter. Both feet and meters are 2 different ways of measuring the same quantity, length. As another example, if we wanted to measure the quantity temperature, we can use degrees Celsius as our unit. Degrees Celsius has a defined size. Alternatively, we can use degrees Fahrenheit as our unit, which has a defined size as well, that's different from degrees Celsius. These are 2 different ways of measuring the same quantity, temperature. Of course, there are other ways or units for measuring temperature, but those are just 2 examples. Now, there are different systems of measurement. A system is simply a convention that's used to measure different quantities. The 2 most common systems are the imperial system, which is also known as the British system, and the international system, which is the modern form of the metric system, and in fact, it's often just called the metric system. For instance, in our distance example, the meter belongs to the metric system, while the foot belongs to the imperial system. And in our temperature example, the degree Celsius belongs to the metric, while the degree Fahrenheit belongs to the imperial. Now, let's consider the metric system. The metric system has 7 base units. The second, which measures time. The meter, which measures distance. The kilogram, which measures mass. The ampere, which measures electric current. The Kelvin, which measures temperature. The mole, which measures amount of a substance, and finally, the candela, which measures luminous intensity. These are called base units because any quantity in science can be measured by those units or units derived from those units. Here's an example of a derived unit. Let's say that you want to measure the quantity speed. Speed is the amount of distance traveled per unit time. So our unit for speed will be some distance unit divided by some time unit. In the metric system, we would use meters divided by seconds. We would write it this way and pronounce it meters per second. Force is another example of a derived unit, which takes the form of mass times acceleration. Using the metric system to define this, our unit of force would be 1 kilogram times 1 meter divided by 1 second squared. In fact, this whole expression has its own name, the Newton. So a Newton isn't a base unit, but rather a derived one. We can go even further than this. The unit for electric charge is an ampere second, which is called the coulomb. The unit for frequency is 1 divided by a second, or the hertz. The unit for pressure is 1 Newton per meter squared, or 1 kilogram per meter second squared, but nobody wants to call it that, so we just call it the Pascal. Torque is force times perpendicular distance, so we get newtons times meters, or Newton meters. The unit for work, or energy, is force times parallel distance, so we get Newton meters as well. But beware not to confuse this with torque, which also uses Newton meters. To avoid this confusion, we say joules when talking about work or energy. There's really no limit to the amount of units that can be derived. You have the radian, steradian, watt, volt, farad, ohm, Siemens, Weber, Tesla, Henry, lumen, lux, becquerel, gray. You get the point. At any rate, those are just some of the basics of units. When taking measurements and making calculations, there are often times when you need to convert between units. Typically, the conversion is from one system to another. For example, you may be required to convert from yards to meters. In this case, you're converting distance from imperial units to metric units. In other times, you may be required to convert between units in the same system. For instance, you may need to convert from inches to feet. Here, you're converting from imperial units right back to imperial units. Let's consider some examples. Let's say that we know the distance from LA to Montreal, which is 2,150 miles, nautical miles that is, by air. And we want to know what this distance is in kilometers. How would we do this? Well, the secret is in the conversion factor. What do I mean by this? The conversion factor is a number you multiply nautical miles by so that you get kilometers, and here's how you get it. First, we find out what 1 kilometer is in nautical miles, or we can even do this the other way around too. The order doesn't really matter, and you'll see why later. But for now, we're just going to go with what 1 kilometer equals in nautical miles, and we see that 1 kilometer is equal to 0.54 nautical miles. So that right there is our starting point. So now, the idea here is, if we want to get kilometers, what we have to do is we have to cancel out nautical miles. To do this, we simply multiply 2,150 nautical miles, our starting point, by 1 kilometer over 0.54 nautical miles. We always want to make sure that the units we're canceling out are opposite each other. So note here how we have 2,150 nautical miles in the numerator, and then we have 0.54 nautical miles in the denominator. So we have nautical miles in the numerator and nautical miles in the denominator. Those will both cancel out. Since nautical miles cancel out, we're now left with kilometers, which means that the number we get after we make our multiplication will have the units of kilometers. So as our final answer, the distance from LA to Montreal is 3,981 kilometers by air. As mentioned earlier, we can do our conversion factor the other way around too and still get the same answer. We said earlier that 1 kilometer equals 0.54 nautical miles. Well, we also know that 1 nautical mile equals 1.852 kilometers, so using this in our calculation, we get the following. We multiply 2,150 nautical miles by 1.852 kilometers divided by 1 nautical mile. Again, notice how nautical miles is in the numerator, and then we also have nautical miles in the denominator as well. So they both cancel out, and then we're going to be left with kilometers. Making this multiplication, we get 3,981 kilometers, just like before. Here's another example. We want to convert from 10 joules of energy to foot-pounds. So here, we're converting from a unit of energy in the metric system to a unit of energy in the imperial system. 1 joule of energy is equal to 0.7376 foot-pounds. To make this conversion, we follow the same steps as in before. So what we do is, we multiply 10 joules of energy by 0.7376 foot-pounds, and then what we do is we divide that by 1 joule. So as you see, we have joules in the numerator, and then we also have joules in the denominator. The joules will cancel out, and we'll be left with foot-pounds. So when we make the multiplication, we have 7.376 foot-pounds. Again, we can do this the other way too. So we know that 1 foot-pound is equal to 1.356 joules. We make the conversion by multiplying 10 joules of energy by 1 foot-pound divided by 1.356 joules. The answer will be the same as in before. Now here's a practical example for you to try on your own. When buying an SD card for a camera, oftentimes manufacturers advertise the card's read speed in megabytes per second. But cameras typically advertise that they record in megabits per second. So what this means is, if you're shopping for an SD card, you have to convert from megabits to megabytes. Megabytes is written with a capital B, and megabits is written with a lowercase b. And we know that 1 megabyte per second is equal to 8 megabits per second. So if your camera records at 100 megabits per second, what would be the required SD card read speed in megabytes per second? So in other words, convert 100 megabits per second to megabytes per second. Go ahead and pause the video to give yourself some time to solve it. Multiply 100 megabits per second by 1 megabyte per second, and then divide that by 8 megabits per second. So what happens is, the 2 megabits per second cancel out, and then what we're left with is megabytes per second. So our final answer would be 12.5 megabytes per second. Okay, so here's where things get interesting with unit conversions. Consider this example. Most desktop and laptop computers have cooling fans installed to keep temperatures from rising too high and damaging the components. Computer fans have different airflow ratings. The higher the airflow, the more air the fan can pull in to keep the computer components cool. These ratings are usually given in either cubic feet per minute or cubic meters per hour. So, how would we derive the conversion factor, given that 1 meter is equal to 3.28 feet and 1 hour is equal to 60 minutes? What we want to do is find out what 1 cubic foot per minute equals in cubic meters per hour. This is a slightly different example than what we've done to this point, because there's an exponent on one of the units. One might think it's just a simple case of doing this, but this is wrong because what we're left with is the units of feet squared meters per hour, and that's not really all that useful to us. What we want is cubic meters per hour. To make this conversion, what we have to realize is that since we're working with cubic feet, we have to cancel out feet 3 times. This means that we have to apply the conversion from feet to meters 3 times. So our conversion from cubic feet per minute to cubic meters per hour will look like this. We'll start by writing 1 cubic feet per minute. Then we'll write our conversion factor from feet to meters 3 times to cancel out the cubic feet. Finally, we'll write our conversion factor from minutes to hours so that the minutes cancel out. So as our final answer, 1 cubic foot per meter is equal to 1.7 cubic meters per hour. Here's one for you to try on your own. Determine the conversion factor for pounds per square inch, or PSI, to Newton per meter squared, or pascals. You're given 1 meter equals 39.37 inches, and 1 pound is equal to 4.45 newtons. Once that's done, convert 92,000 pascals to pounds per square inch. Again, go ahead and pause the video to give yourself some time to make this calculation. Alright, let's solve it. First, let's get our conversion factor. To go from pascals to Newton per meter squared, we set up our units like this. First, we write pounds per square inch. Then, we cancel out the pounds. And after that, we cancel out the square inch. To do this, we have to cancel out inches twice because it's squared. When we make our multiplication, we get 6,897 Newton per meter squared. So this means that 1 pound per square inch is equal to 6,897 Newton per meter squared, or pascals. Now that we have our conversion factor, let's convert 92,000 pascals to PSI. Since we know that 1 PSI is equal to 6,897 Newton per meter squared, or Pascal, we multiply 92,000 Newton per meter squared by 1 pound per square inch, and then we divide that by 6,897 Newton per meter squared. This ensures that we have a Newton per meter squared in the numerator, and we also have a Newton per meter squared in the denominator. The 2 newtons per meter squared cancel out, and we're left with pounds per square inch. Making this multiplication, we get 13.3 pounds per square inch, so that means that 92,000 pascals is equal to 13.3 psi. Up to this point, we've been converting between units of the same quantity. In our yards and meters example, we converted from yards, a unit of distance, to meters, also a unit of distance. And in our most recent example, we converted between pascals and psi, which are both units of pressure. Of course, this is intuitive, but sometimes we want to convert from units of one quantity to units of a completely different quantity. Take this example. So in commercial aviation, when ground crews refuel airplanes, they typically record the amount of fuel they add to the planes in either gallons or liters. These are both units of volume. However, the pilots are concerned about the aircraft's total weight. Therefore, they record the amount of fuel added in pounds, a unit of weight. What this means is that volume of fuel added to the plane has to be converted to pounds for it to be useful to the pilots. 1 liter of jet fuel is 1.77 pounds, and 1 gallon of jet fuel is 6.7 pounds. The conversion process is the same as before, so if you're a pilot and you want no more than 11,000 pounds of fuel, how much fuel in gallons should the ground crew put in? We multiply 11,000 pounds by our conversion factor, which is 1 gallon divided by 6.7 pounds. Again, we're making sure that we have pounds in the numerator and in the denominator, allowing them to cancel out. And when we make our multiplication, we get 1,642 gallons. We could also convert from, say, gallons to kilograms, or liters to pounds, or liters to kilograms. It doesn't really matter, you just have to be mindful that you're using the correct conversion factor. Because something as small as using an incorrect conversion factor can lead to things like getting an answer wrong on a test, to something more serious like the Gimli glider accident. Gimli glider was an aviation accident back in the early 80s involving one of Air Canada's brand new Boeing 767s. On a flight from Montreal to Edmonton on July 23, 1983, the plane ran out of fuel midway through the flight. Both engines shut down, effectively turning the airplane into a glider. The plane couldn't make it to Edmonton. Instead, they had to divert to a retired military airstrip in Gimli, Manitoba. The pilots navigated their way to Gimli, but the landing gear failed to deploy properly, meaning a crash was imminent. The pilots were able to crash land the airplane onto the short airstrip, and miraculously, all 69 people on board survived. Despite the plane crashing onto the runway, only some minor injuries were sustained, and get this, the injuries didn't even come from the crash itself, they came from the passengers escaping down the very steep slides. The investigation that followed revealed the plane only took off with half the fuel it needed because an error was made when making the conversion in a calculation from volume to weight. The brand new Boeing 767s were the first planes in Air Canada's fleet to switch to kilograms as the unit for the fuel's weight. But ground crews were still used to converting the volume of fuel to pounds. The plane needed 22,300 kilograms of fuel for the flight, but because the wrong conversion factor was used, the plane took off with 22,300 pounds of fuel, just under half the fuel it needed. And this just goes to show just how important using the correct units are. Another example of this is the Mars Climate Orbiter. The Mars Climate Orbiter was a robotic space probe sent to Mars to collect data on the Martian atmosphere. However, as the probe went into orbit, NASA lost communication with it because ground-based software monitored its angular momentum using imperial units of pounds/seconds, instead of what the probe used, which was Newton seconds. The probe went into a much lower orbit than expected and either burned up in the atmosphere or crashed into the Martian surface. Let's briefly talk about metric prefixes. Metric prefixes are used on metric units to make it easier to write really big numbers or really small numbers. For example, we usually wouldn't want to say 0.002 meters. Instead, it's just easier to say 2 millimeters. Similarly, it's much easier to just express a frequency as 21.36 gigahertz than it is to write 21,360,000,000 Hz. Refer to this table for a list of some metric prefixes. Of course, this isn't an exhaustive list as there are more metric prefixes for bigger and smaller numbers than shown here, but for this video, this table will suffice. As a general rule, if the number is greater than 1,000 or greater than 0 but less than 1, it's probably a good idea to use a metric prefix on the unit. You want to use a metric prefix that allows you to write the number in such a way that it's between 1 and 1,000. 0.002 meters is between 0 and 1, so we use a metric prefix, milli, that allows us to write the number so that it's between 1 and 1,000, in this case, 2. 21,360,000,000 is much greater than 1,000, so we apply a metric prefix, giga, and this allows us to write the number as 21.36. As you can see, it's between 1 and 1,000. The conversions for a non-prefixed unit to a prefixed unit work on the same principles as discussed earlier. Consider this example. We want to convert a 26,771 gram brick to kilograms. How do we do this? Well, we look onto our metric prefixes table. We see that 1 kilo is equal to 1,000. Therefore, 1 kilogram is equal to 1,000 grams. That's our conversion factor. Since we want to convert to kilograms, we want to cancel out grams, so we set up our conversion factor in such a way that we have grams in the numerator and we also have grams in the denominator. In this case, we'll multiply 26,771 grams by 1 kilogram divided by 1,000 grams. Grams cancel out and we're left with kilograms. This means we know that we've applied our conversion correctly. Making our multiplication, we get 26.771 kilograms, or rounding, we get 26.8 kilograms. How about this example? Let's convert 287,500 centimeters to kilometers. From our metric prefixes table, we know that 1 kilometer is equal to 1,000 meters, and we also know that 1 centimeter equals 0.01 meters. Let's use this information to find out what kilometers is in centimeters. We set up our equation in such a way that meters cancel out, so that we're left with kilometers and centimeters. As you can see, we get 1 kilometer over 100,000 centimeters. What this means is that 100 kilometers equals 100,000 centimeters. This is our conversion factor. We then apply this to 287,500 centimeters. Making our multiplication, we get 2.875 kilometers. Finally, we're going to talk about uncertainty, which is also known as error. In a practical setting such as in a lab or an engineering application, that is, when you're actually taking measurements, the uncertainty of those measurements should always be considered. This is because it's physically impossible to take an exact measurement. We're limited by the measuring tool we use. This means that there'll always be some level of uncertainty in that measurement. Let's consider an example. Let's say that you measure the mass of an object and it gives you a reading of 304.3 grams. The reading you get on the scale is limited by the amount of decimal places and digits that the scale gives you. In this case here, the scale gives us a precision of no more than 1 decimal place, leaving us uncertain as to how much the object weighs beyond 1 decimal place. So how do we express uncertainty then? Well, this is how you do it. As a general rule, the uncertainty is plus or minus half the smallest measure. In other words, half the smallest possible reading the scale can give us that isn't 0. In this case, the smallest possible non-zero reading that this scale can give us is 0.1. Half of 0.1 is 0.05. Therefore, our uncertainty in this case is plus or minus 0.05. Now let's say that we got another scale, and this scale is more precise than the other one. This new scale gives us a precision of up to 2 decimal places. So, let's say that we put the original object onto this new scale, and we get a reading of 304.32 grams. What would be the uncertainty here? Again, the uncertainty is plus or minus half of the smallest non-zero reading that this scale can give us. The smallest possible reading that this scale can give us is 0.01 grams. Half of that is 0.005 grams. This means that the uncertainty is plus or minus 0.005 grams. Okay, so far we've dealt with single measurements. Now, let's see what happens to uncertainty when we take multiple measurements. Let's say we measured the mass of one object, and it gave us a reading of 312.1 grams. We then measured the mass of another object, and it gave us a reading of 202.8 grams. And finally, we measured the mass of a third object, and it gave us a reading of 211.0 grams. What would be the total mass of all three objects and the uncertainty? The total mass is simply the sum of all three masses, which is 725.9 grams. But what about the uncertainty? The smallest possible measure on this scale is 0.1 grams, which means that the uncertainty for each reading will be 0.05 grams. The total uncertainty is simply the sum of all the uncertainties, so in this case it will be 0.05 grams plus 0.05 grams plus 0.05 grams. This gives us 0.15 grams. So our final answer will be 725.9 plus or minus 0.15 grams. As you can see, the uncertainty increases with every single measurement. This is called propagation of error, or propagation of uncertainty, because uncertainty, or error, accumulates with every single measurement, and this is not ideal. In this scenario, we can definitely minimize the uncertainty. To do this, we simply measure all three objects at once, and what this will do is will give us an uncertainty of 0.05, because we're only making one measurement. Now keep in mind, the scale could also read 725.8 grams or 726.0 grams. This is because of uncertainty. When we measured each individual object one by one, the scale had to round either up or down to the nearest tenth. This means that we lost some information in the process. The 312.1 gram object could have been rounded up from 312.09. The 202.8 gram object could have been rounded down from 202.84 grams. The 211.0 gram object could have been rounded down from 211.04 grams. Adding up these more precise numbers, you get 725.97 grams, and on a 1 decimal place scale, this just rounds up to 726.0 grams. This is why if you measured all three objects at once, you could get this number. Similarly, rounding errors in the opposite direction is what could get you a reading of 725.8 grams. And this is what an uncertainty of plus or minus 0.15 grams means. It means that the actual value of the mass ranges somewhere between 725.9 minus 0.15 grams to 725.9 plus 0.15 grams. All that being said, the biggest takeaway here is that the fewer measurements taken to get a total value, the lower the uncertainty will be. This is another advantage of using a tape measure to measure long objects instead of taking multiple measurements with a ruler. Because other than the fact that taking multiple measurements with a ruler is tedious, you also accumulate lots of uncertainty. Whereas with a tape measure, you only take one measurement, thus minimizing the uncertainty. And speaking of rulers, let's say that you have a ruler which has millimeter markings. You use that ruler to measure the length of your laptop. You get a reading of 22.6 centimeters or 226 millimeters. What is the uncertainty? You might have to think about this one for a second, so go ahead and pause the video. Think you got it? Alright, let's find out. When you're taking a measurement with a ruler, you're referencing that object in two spots on the ruler. The 0 mark and the end of whatever you're measuring, in this case, the 226 millimeter mark. This means that we're accounting for two uncertainties. The smallest measure on this ruler is 1 millimeter. Half of that is 0.5 millimeters. Since we have uncertainty in two places, propagation of uncertainty kicks in. This means that we have to add both uncertainties, giving us a total uncertainty of 1 millimeter. Therefore, our final answer will be 226 plus or minus 1 millimeter. The rule for propagation of error works with subtraction as well. That is, if you're subtracting measurements, you are still adding uncertainty. Let me explain with this example. You have liquid in a beaker measuring at 120 milliliters. You then pour out some of the liquid and remeasure. You get a reading of 90 milliliters. How much fluid in milliliters did you pour out, and what's the uncertainty? Well, 120 minus 90 is 30, so we know that we poured out 30 milliliters. What about the uncertainty then? Well, on this beaker, the smallest measure is 5 milliliters. Half of that is 2.5 milliliters. Therefore, our uncertainty for each measurement will be 2.5 milliliters. Notice that while we're subtracting 90 from 120, we're not subtracting the uncertainties 2.5 and 2.5. Instead, we're adding them. Again, this is because error propagates with each measurement. It doesn't decrease, and it's impossible to have zero uncertainty. So, we've just talked about the propagation of error rules for addition and subtraction. But what about multiplication and division? Let's say that you want to find the current going through a resistor. The current I is equal to the voltage V divided by the resistance R. Let's say that we measure the voltage and resistance on this particular circuit. You take a multimeter and measure the voltage. You get a reading of 25.2 volts, and then you take the multimeter and measure the resistance, obtaining a value of 101 ohms. For the voltage, since the smallest reading we can get in this scenario is 0.1 volts, the uncertainty is 0.05 volts. For the resistance, on the other hand, the smallest value we can get is 1 ohm. Therefore, the uncertainty is 0.5 ohms. To get our current, we divide the voltage by the resistance, and this gives us 0.25 amps, or 250 milliamps. But what about the uncertainty? For our addition and subtraction examples, we got the final uncertainty by simply adding the uncertainties of each measurement. For multiplication and division, however, what we have to do is we have to add the percent uncertainties. We can then convert this back to an absolute uncertainty, and this is how you do it. The percent uncertainty of a measurement is equal to the uncertainty divided by the measurement times 100%. So for the voltage, the uncertainty on that measurement was 0.05 volts. The actual measurement of the voltage was 25.2 volts. We then multiply that by 100% and we get 0.198%. And this is the percent uncertainty on the voltage. Now, how about the resistance? Same process. The uncertainty on the resistance is 0.5 ohms, divided by the value of the resistance, 101 ohms. Multiply this by 100% and we get 0.495%. We then add the 2% uncertainties. This gives us 0.693%. This means that in theory, we could write our final answer as 250 milliamps plus or minus 0.693%. However, the percent uncertainty isn't all that useful to us, so let's convert it back to milliamps. Our final uncertainty is 0.693% of 250 milliamps. So what we do is we multiply 0.00693 times 250 milliamps. Our answer is 1.73 milliamps. We can then round this to one digit, and as a result, we get an error or uncertainty of 2 milliamps. So we can write our answer as 250 plus or minus 2 milliamps. Let me conclude uncertainty by talking about why uncertainty is plus or minus half the smallest reading in the first place. When taking a measurement using an analog device, such as measuring the length of an object using a ruler, we intuitively round our measurement to the nearest tick. In this example, the object we're measuring is closest to the 10 millimeter mark than any other mark on the ruler. In other words, it's no more than half a millimeter past 10 and no less than half a millimeter below 10. This is why we'd record this measurement as 10 plus or minus half a millimeter. Similarly, this reading would be recorded as 11 plus or minus 0.5 millimeters because the end of the object is closest to the 11 millimeter mark. Now, when taking a reading off a digital device as opposed to an analog device, we're still going to be using plus or minus half the smallest reading. The device automatically rounds to the nearest reading for us, so all we have to do is we just have to add the uncertainty of plus or minus half the smallest reading. Now, to solidify our understanding of this, let's look at an example of a digital device where this rule wouldn't apply. I'm talking about a clock. This clock here reads 11:32, and the smallest reading on this clock is 1 minute. But a clock doesn't actually work by rounding to the nearest minute. If the time was, say, 11:32 and 40 seconds, it simply wouldn't just round up to 11:33. Even if the time was 11:32 and 59 seconds, the clock still would not round up to the nearest minute. It would still read 11:32. The time changes to 11:33 only after all 60 seconds have passed. Therefore, plus or minus half the smallest reading cannot apply to a clock. Instead, you can sort of think of the uncertainty on this particular clock as plus 1 minute. That being said, we typically don't concern ourselves with uncertainties on clock readings. However, this was just merely to demonstrate why uncertainties on most readings are plus or minus half the smallest reading. In practice, numbers are not very useful to us without context. Units provide us with that much needed context, allowing us to make sense of the numbers we're looking at. And this video is just an introduction to some of the skills involved with working with units. As demonstrated, it's always important to pay particular attention to the units you're using and to take great care in ensuring that your conversions are correct. Converting between units is a fundamental skill in engineering and science, but it can also be very useful in day-to-day life. Metric prefixes are a convenient tool to use when working with very large or small numbers in a practical application. And finally, understanding the limitations of your measuring devices and communicating it through the use of uncertainty is of equal importance. But that concludes it for this video. I hope this video helped you understand the basics of working with units.